Hi guys, today we're going to look at AS on states of matter. We basically will be doing ideal gas. The first one, of course, is this thing called the assumptions of kinetic theory. Mainly for gas first, okay? And also we will talk about Boyles Law and how we apply in problems and in graphs. All right? So the study here is states of matter, study of particles in solids, liquids, and gases. Basically, all some gases today. Interactions between them is important for the understanding of physical properties and so forth. Okay, candidates should be able to, the one, gaseous state, ideal and real gas. Basically, talk about ideal one first. And P equals nRT, the equation for calculation. Firstly, state the basic assumption of the kinetic theory as part of ideal gases. Okay, it's only for ideal gases. So if it's real gas, it will be, it will be deviation, right? So here, talk about explain qualitatively in terms of intermolecular forces and molecular size, the conditions necessary for gas to press ideal behavior. Limitations at very high pressures and low temperature we will come across later, and we will use this one, state the use of general equation for N equals MRT, okay? In terms of MR. So we would use this, we will finish the whole thing, except maybe if we don't have time, we won't do this one here. Okay, basic assumptions of kinetic theory, right? And in Form 5, we did actually for this kinetic theory. Kinetic theory talks about particles, and particles of elements and molecules same. Elements means they all contain the same type of substance like sodium, potassium, calcium, oxygen. Okay, if it is for compounds, they talk about like copper oxide or copper carbonate. Okay, so whether in liquid gas, solid, liquid gases, they will have certain theories about them, certain assumptions. First, of course, motions. In Form 5, that all the solids they just rotate. Some people say vibrate, but they don't move. You see, they are stationary. So this is vibration, rotation is they are stationary. Okay, stationary, they don't move. Okay, immobile, they call it immobile. Okay, but for liquid, they actually vibrate, rotate, and transit, which means they move. But they will slide each other. They slide over each other. Okay, this is the thing you use. Okay, each other in your Form 5. They will touch each other. Okay, here, well, they rotate, they vibrate, and they don't touch each other. Okay. No touching, it is far apart, okay? Far apart. Okay, you see the no touching is here, right? Particles contact, close packing. Of course, it's called lattice. T-T-I-C-E. Okay, hold on now. Let me just put on the time first. 11, 10. Okay, particles contact by motion. I said the word they use is slide. Okay, they slide over each other here in Form 5. Here they don't touch at all. The distance is very far. Okay, further than the molecular size, they would say. Energy is the lowest of all, not zero yet. You learn about zero and enthalpy and entropy later. Okay, here's medium and here's high energy. Intermolecular forces, here's the greatest of attraction because they're close to each other. Okay, they're basically ionic, covalent, or metallic. Here, hydrogen bonds and metal forces occur. Okay. Here, no. We assume that there's no intermolecular forces in gases for ideal gas. Of course, for real gas, you'll find, well, they do have some, okay, which we talk about later. Order, this is for entropy, most ordered, some disorder, and most disorder. You come across it later when you do your entropy, okay? Right, now there are a few assumptions here. I got 4, some people put 5, don't care. Right, the kinetic theory of gases, remember this of gases. Right, basically of gases, right? So the first thing is matter made of particles. The particles are the smallest size of anything. Okay, if it's element, it's called atoms. If it's compounds, some molecules. But also elements can be called molecules like O2, O3, S8. Anything that has got diatomic, triatomic, or whatever. P4 can become more molecule. Okay, so ions, particles. Now here is gases. All gases are considered pinpoints. Therefore, the volume are negligible. The key is they are negligible compared to the total volume. Very important, negligible compared to total. Now, I just want to stop a while here and show you a problem. It's a very good problem. Okay, came up before in your A levels. Let's show you here. Let's go here. Okay, here we are. This is what? Okay. Now, of course, here we come to this one after two assumptions of kinetic theory, right? And again, now here. How many atoms of argon are there present in 1 mole? Like done before, of course, it's 6.02 10 to the power of 23. A lot of it atoms. Remember? They are atoms in 1 mole. Okay? You have to calculate the percentage of volume occupied by atoms themselves in 1 mole of argon at room temperature and pressure. So RTP here would suggest that the temperature is 25 degrees centigrade and pressure is equal to 101,000 pascals, okay? Or some people say 1 atmospheres, but this is more important when used for calculation, pascals, okay? Or kilopascals will be 101 kilopascals. But Pascal is more important because of the R for calculation, okay? So use the data book to calculate the volume of 1 atom of argon. Now, 1 atom, we assume it is, well, spherical. And of course, from the data booklet, you can see from here, yeah, I didn't go back yet, huh? Never mind. Rotate. Sorry, I missed the whole thing. Never mind, we can go down here again. Okay, now here we are, argon, right? Argon given here, you need to know how to use the data booklet. Okay, atomic radii, yeah? I mean the radii is nanometers. Argon is here, 0.190, okay? I can see the marking scheme put wrong, 19. Sometimes I put 0.192 as the marking scheme, depending on the data booklet they give you, okay, right? So here's 192, let's say 192, because the marking is 192. So radius of argon, 0.192 nanometers, okay? Let's say, because I see the marking scheme, so I know, right? So here's the radius. So the volume of per atom is 4/3 times pi is 3.14 times, of course, now nanometers, right? 1 to the power of minus 9, or 9 nanometers is equals to 1 meter. Okay, so changes to meters will be 0.192 times 10 to the power of minus 9 meters. Sorry about this. Meters, huh? Okay. Okay, so it is cube. Okay, now. So the changes will be this end, right? Now, this is the one here. Now look at the marking scheme, huh? Right? Easier, I don't have to. Okay, so now here wrong, okay? You know, Cambridge put wrongly. You can do a calculation and get the correct one. Okay, so see it is 0.192. Okay, now this is the amount, right? And it should be 29, which is correct. Okay, right now you want to do in dm cube, very simple. Now I got all the things here, 100 meters to the power minus 9 meters. Okay, right? So to change it to meters, you just times this one, right? Now 1 meter, 1 times 1 meter times 1 meter equals 1 cube. Now to change to dm cube, 1 meter is equals to, right, 10 dm, isn't it? 10 decimeter, right? So change to 10 here, 1 dm cube, so 1 meter cube, so the power of 3 dm cube is 1. Okay, so to change this meter to dm cube, you just times 10 to the power 3, which gives you 10 to the power 29 to 10 to the power 26. Okay, so either way you can do, you need to learn how to convert properly. So this is the best way of conversion. Okay, right? After this is cm cube as well. Okay, for of course cm cube is 100 cm cube. Cm is 1 meter cube. 1 meter, sorry. So 1 meter times 1 meter times 1 meter equals to 1 meter cube. So change to cm will be 100 cm times 100 cm times 100 cm equals to 1 meter cube. So 10 to the power of 6 cm cube equals to 1 meter cube. Okay, you see this afterwards. So this is one of the easiest way to remember, how to convert, not to remember, except to remember that 1 meter is equals to 100 cm cube. 1 meter is equal to 10 meter cube. 10 meter, 10 dm, sorry, decimeter. Okay, so from here you can see, right, this is the this will be the volume, very small volume for one atom. So they ask you here, right? So use your answer and see to calculate the volume of 1 mole. So if one atom, right, have got this amount of volume, so 1 mole is 6.02 to the power of 23. 23 atoms will contain this over 1 times 6.42 and to the power of about 23, right? Which is here. Make it easier, okay? Right? See, times this. So this value here times your Boyle's number. So we give it this one here. That means this is the total volume occupied by 1 mole of argon. Okay? Can be meter cube or dm cube, up to you. Dm cube is easy to calculate. So very small, is it? Now remember they ask you here, well, right, what's the volume occupied by 1 mole of argon, assuming ideal gas? Of course, 1 mole of any gas, right? 1 mole of any gas. Remember, any gas at RTP occupies what? 24 dm cube. That's why 24 dm cube is easy to use. Okay? So percentage of volume occupied by atoms will be the volume of here over 24, isn't it? Right? So here, the volume, right here. Okay? The volume of, the total volume of 1 mole of argon over 24 is only 0.074%. It's very small, isn't it? So the volume occupied by the gas compared to the actual volume occupied is only 0.074, which means there are a lot of empty space here. Okay, so you can actually say that the volume compared to the whole volume it occupies, can say the volume of the gas is negligible. It's even say 0, no? Okay, so that's why you say here, explains your justify your assumption. And what's the assumption? 2 assumptions here. Now let's go to the assumption. Okay, you say what? Right, see, the volume, the volume of the gas as occupying in this container is negligible compared to the total volume now. 0.074%. You can even say the volume is equal to 0. Okay? Now let's go a few more. I'll show you how the questions come out. Okay? Particles of gas move in a continuous rapid random motion. That means they knock each other at random. That's why diffusion occurs. And the pressure of the walls of the vessel is due to the gas bombarding against the wall. Okay? And the pressure is proportional to the number of moles, not the mass, by hitting the gas. Why? Because now this is very important. You see, if I were to talk about, I told before in the other part, let's say if I've got a container here. Okay? Okay, let's say I put RTP, okay? Temperature equals to 25, okay? Temperature is equals to 1.1 kilopascals, okay? Right? Kilopascals. So this will be pressure equals to 101 kilopascals, okay? To put this correctly. And temperature is equals to 25 degrees centigrade. If I put 1 mole of gas, 1 mole of, let's say, lightest gas is hydrogen and H2, okay? Right? It's like here, which is mass is equals to 2.0 grams. And the volume occupied is 24 dm cube, isn't it? Yes? And it contains 6.02 to the power of 23 molecules of H2. That's not 1 mole, that's not 1 mole. Contains this number of particles in. Now if I put a heavier gas, okay, heavier gas, all right, so here, let's say I put nitrogen, 1 mole of nitrogen, which is how much? 28 grams. Mass is equals to 28 grams, 0.0 grams. Heavy gas, right? And well, the pressure also same, 101 kilopascals. Temperature same, 25, right? The volume occupies the same because according to the law, right, of this gas, right, this is also 24 dm cube. 1 mole 1 mole of any gas, 1 mole of any gas at RTP occupies 24 dm cube. Any gas. See, the gas particles here is heavier, N2, and the number of particles here is how much? Same, 6.02. So the number of molecules here is the same. Okay, right? Of course, in this case here, this hydrogen here is knocking against the wall. First, lighter substance, not lighter, okay? Right now, this heavier fellow, not heavier, isn't it? But this H2 moves at a faster speed. So move at a slower speed, isn't it? So the impact is about the same. Remember, this hydrogen is lighter, it moves faster. Of course, the velocity is faster. But the heating of the wall, right? The pressure and the heating of this lower fellow but larger mass in the wall produce the same pressure. So the pressure is caused by the particles hitting against the wall. But the total pressure is independent of the mass. Depends on the temperature, okay? And of course the velocity. So remember here, the pressure is due to the particles hitting the wall and also due to the mass and also due to the velocity. So, but for here, we suffice to say that the pressure is due to the number of particles. The temperature remains constant, okay? So if the number of particles same, the pressure is same. Okay, very important, huh? So this is it. So gas move at random rapid motion. Okay, this is what you want to mark here. Pressure, of course, is to understand caused by the particles hitting against the wall. And I say pressure is proportional to the number of moles, not the mass. Okay. The next one, of course, is gas particles are separated by a large distance. Therefore, assume no intermolecular attraction, no hydrogen bonds, no van der Waals forces. Okay, but of course, it's not true. At very high pressure and very low temperature, they will have. That's why they will deviate from the ideal gas law. You will see afterwards. Okay, collisions are perfectly elastic. Okay, right? They hit one another. There's no loss in energy. Therefore, average kinetic energy of any gas is constant given temperature. Okay, increase in temperature causes increase in Ke. Now, this is very important later when you do your Boltzmann distribution. Okay, but let's look at how the question comes out. Okay, right. Now I got a few here. Assumptions. All right. Calculation I've done with you. Okay, 55. See here. Okay, assumptions. Now here 2. State the assumption of ideal gas behavior. 2 here. Now this is a later one. Okay, 2 here. Right. Volume of a gas molecule or volume of gas atoms or particles is insignificant compared to the volume of the occupies the vessel. You must say compared to. Okay, you must say compared to. What is this? Okay, see. Compared to the volume of the vessel that the gas occupies. Right? Smaller. Huh? Okay, so it's insignificant. Or the other one said here, right? Here, this is the first one. The volume of the gas particle, the volume of the gas molecules is negligible compared to the volume of gas occupies in the vessel. See now, okay? So the volume is taken to be 0 or no. And later you see, insignificant or negligible. Both these words are being used. Second one, there are no intermolecular forces between them. Okay, no van der Waals forces, no hydrogen bonds. It means they are free from all interactions. No intermolecular forces. Okay. Or the collisions are perfectly elastic to you, right? The particles are in constant motion. No energy is lost. Okay, 82. Right? And the other one is about the same. 2 marking same. No forces of attraction between the gas molecules. All collisions are perfectly elastic. 82. So learn 3. Cukup. Right? Now, of course, this one here. Right? So now I'll give you another one first before we go to this one. 57. Okay, look at the different way they actually ask you. Right now here, 31. What are assumptions of kinetic theory of gases and hence the ideal gas equation? Now this is called the ideal gas equation, which you learn in Form 5, right? Because in NRT, we should learn earlier to calculate the MRs now. Okay, because PV equals to mass over MR. This is the number of moles in, right? To use again. Right? Molecules move without interacting one another. Correct, isn't it? It means that they move at random. There's no intermolecular forces, which is correct. Intermolecular forces are given, correct. Intermolecular distances are much greater than, which is correct. Okay, so this is how they rephrase it. Okay, 57 finished. Now last one, 74. You can see how they rephrase the English words. What are the basic assumptions of kinetic theory applied to ideal gas? Okay, ideal gas means ideal gas, which means that the kinetic theory is correct. It's true. That means the assumptions here are true. Gas particles are in continuous random motion, right? Gas particles experience no particles, which is correct. So the volume of each particle is 0. Okay? All is correct. This answer is A. 1, 2, 3. Okay? Okay, now we have done the assumptions. Now let's go now to the actual Boyles law. Okay? Now remember there are 3 laws here which are used. Like I said, 3 laws of gases which are used. Boyles law, Charles law, and Douglas law of partial pressure. We will do this even though it's not mentioned in your syllabus, but they do ask Douglas law of partial pressure. Okay, because it's application of the ideal gas law. Boyles law, Charles law, and partial pressure. Okay, let's see how we deal with each other. Now, Boyles law first. Remember, in any gas situation, let's say the gas occupies volume, isn't it? So why is there volume and gas? Now, a gas we have got 4 variables, 4 things that will be controlling the properties of a gas, or the physical properties. Okay, gas. Well, gas. They're called variables. Variables which you can change. First, of course, if you pump the gas out here, they occupy volume, isn't it? So, well, number of moles first. Number of moles of the gas. Secondly, of course, it will occupy volume because gas occupies volume. Okay, volume of gas. Thirdly, of course, then because of the particles hit against the wall, create a pressure. There'll be a pressure. Okay. Secondly, of course, the temperature will affect it. Yes, temperature will affect it. Okay, because temperature, the higher the temperature, the more it will hit. Pressure, volume will change. Of course, there's this thing called R, which is a gas constant which you need to apply. So 4 things. Okay, so it's like PV equals to nRT. Okay, 4 things. So of course, other than R is a constant, there are 4 things can change. 1, pressure, volume, number of moles, temperature. All this will be interconnected. We change one of these things, the other will change. Okay, now Boyles law, to study Boyles law, we keep 2 things constant. What is it? A given mass. Given means given, it cannot change. Okay, or the number of moles. Number of moles is given. Okay, don't change, constant. And temperature is constant, or given, given temperature. So the word given means that you don't change. So you don't change 2 things, N and T. So for Boyles law, these 2 are held constant throughout the experiment. Held constant throughout the experiment. Okay, throughout. An experiment means what? Means you change the 2 things. What you will change? Volume. So Boyles law talk about changing volume, change, and when the volume change, the pressure will change. Okay? Change. How do they change? Of course, by common sense. You put 1 mole of gas in the container, constant temperature, you increase the pressure, of course the volume will decrease now, right? That's the idea. But how does it change? So Boyles law states it out this way. The volume of a given mass of gas is inversely proportional to the pressure when temperature is constant, which means that it says that, well, the volume is inversely proportional to 1 over P. Okay, 1 over P is inversely proportional. Temperature and number of moles constant. Okay, so how do they prove this? Very simple, right? Now, of course, here, of course, 1 and 2 is before and after, they will be the same temperature. Okay, now here I put out here because they ask you to draw graphs. Now, this is supposedly like this is fictitious, of course. Let's say for this experiment, okay? This experiment here, I'm going to put red ink to show the difference. Okay, let's say this guy did experiment here. Boy did this experiment. Okay, he put, let's say here, the number of moles here is equal to 0.1 mole. Okay. The temperature he kept at 25 degrees centigrade. Okay, it's two constant, and that's the pressure gauge here. Okay, sit on it, pressure. So when he found that when the pressure is 1 atmosphere, right, the volume here is equal to 1 dm cube. Let's say, okay, this is the first experiment. Experiment 1. Okay, experiment 2. He increases by 2. Right? There, of course, the volume will decrease. He found the volume to be 0.5 dm cube. Okay, and to 3. Subsequently, the volume will decrease 0.33 and so forth. Okay, 4 and so forth. So we got these are the initial values of Boyle's experiment. Remaining what, same number of moles and temperature same. Okay, so now he first plot the graph of P. Actually, it should be V against P, but some other books P against V. Don't care, okay? Because this is the x-axis, right? You are changing here. This is the responding up, right? The result. So when the P is low, right? 1, of course, the volume here is 1 now. Okay. When the P is 2, about here, right? 0.5. P is 3 and so forth. So you get a current, which is inversely proportional. It's not, right? Okay. So P is inversely proportional to 1 over V. Yeah, what is this? 1 over V. Right? Where T and N constant, you don't change. Or you can say P proportional to 1 over V, up to you. It's called inversely proportional. Inversely proportional. Okay? That is Boyle's law. Okay, now they ask you to plot something, or better still, they ask you to plot something here. PV against P or V. Now, so I got down here, if I remember this is the initial one. So PV against P or V. 1 times 1 is 1. 2 times half is, okay, it's 1. 2 times 1 over 3 is 1. So they all give you constant. That means you plot the PV against change of P, it will give me a straight horizontal line that's parallel to your x-axis here. Okay, this is what I asked. Next one, of course, I ask this one here. P against 1 over V. Okay, with 1 over V. Okay, remember P is constant here, they don't change here. V of 1 over 1 is 1, 1 over 0.5 is 2. Because 1 over half is 2, isn't it? 1 over 3 is 3. No, see? 1 over 4 is 4. So remember, they will increase directionally. That's right here. Okay, right? So 4 graphs. Now, interestingly, this graph is given PV against N. Nothing new to you. Okay, now let's look at the page 65. So I can introduce you to the graphs that is given in exams. Okay, now look at here. Which again shows the correct graph for PV of an ideal against N. All right, remember, right? Remember, if it's P, if it is what we normally learn is P against V. Okay, is like that, or V against P is also the same. Okay, or PV against P, or V is straight. But now it's against N, you know. Okay, obviously you can look back at the equation PV equals to nRT, isn't it? Okay, so PV over RT equals to N. Temperature remain constant, not constant temperature. This to a constant. Of course, when the number of moles here, when you increase the number of moles, okay, right? Pressure and volume will also increase, isn't it? It's not. Yeah. Yes. So of course, which is correct here. So when this increase, this will also increase. So at 0 moles, of course, it's 0, 0, 0. So this is the correct one. So you use this equation, this N here, N. Okay. All right. Now another graph, another graph, 65 is 66 here. Remember now this V is this is a normal one. See? They put P against V against P1. Because as you change P, the volume will change. See? Which diagram shows you the correct V against P for fixed mass. See? Fixed mass and the constant temperature. So these two, number of moles and temperature is constant. Okay? So the change is volume and pressure. Got it? Okay, now this is as far as I'm going to go here. Right? Now let's go back to Boyles Law. Okay? So you can see how this thing will affect your graph. One more, the graph is of course density. Okay, now let's go density first, okay? Okay, let's go up here. Okay. Right. Now here I want that rho is density, okay? Right, now this one I've done it, okay? And rho V, right? Something will come out. Obviously it comes quite a lot. Okay, 1 over V is, that means 1 is to 1 in a straight line here. Okay, a little, okay? Wait, here was. Let's do this one first now. 1 over rho P. Okay? Now, density. Remember, density is mass over volume. For a given amount of mass of gas, the mass don't change. But as I increase the pressure, the volume will decrease, isn't it? So of course, density will change, right? Increase the pressure, the mass remains constant, the volume will become smaller. Smaller, same mass, of course, the density will increase. That's all. Okay. Now, how do they show it in the diagram or in the equation? Remember, now this is the ideal gas law. P equals nRT, changes N to number of moles mass over mR. Okay. Now change this again. I bring this one down here. I bring this whole thing down. Okay, this whole thing. This one up and down here. I want to get a mass. Okay, I'll put the thing. Well, let me show you here. Okay, PV equals to mRT over mR. Yeah. Okay, I want to bring the V down here because why? I want because density is equal to rho. I better write properly. Rho. It's called rho. Okay, this rho. Rho. Okay. Rho is equal to mass over volume. This is density. Okay. So I want to put M here over bring down V. It's equal to rho. It's equal to what? P, mR over RT. Yep. Okay. So this is rho. Now, of course, if I want to bring P down here, so it's rho over P equals to mR over RT. So this thing will change, obviously, right? mR is constant, right? For temperature is constant. Temperature constant. Remember, the number of moles and temperature is constant. For what? For Boyles law. Okay. R is a constant. So all these are constants. Right? So if I change the P, if I increase the P, when P increases, obviously the density will also increase in. Why increase? Because the mass is constant, the volume will decrease in. So increase. So increase will cancel each other. That means that they should give you, as you increase the pressure, it gives you a straight line like this. So straight line, constant. Here, of course, equals to what? mR over RT. That means the temperature and the mR of the gas will affect the value here. R remains constant. Okay? So this is what they actually test you on. Okay? This line here. Now let me show you a question on this, okay? On density 58. 58. Right here. Okay? You can see that? Bigger. Smaller bit. Which equations apply to an ideal gas? P is pressure, V is volume, M is molar mass, rho, that's the concentration, which means mass over volume. Okay, R is gas constant, and so forth. Now remember this one, remember? See now, this, if you put it the other way, is rho over P is equals to what? MR over RT, isn't it? Which is correct. Yeah, this is correct. Okay, this of course is wrong. Okay, right? Where's the rho? Okay, because this one is what? N, is it? That's the number more. That's also wrong. Because C is what? Mass over your volume is V squared. So this is the only one correct. Okay, you can work it out yourself. Now let's look at other kind of questions. Okay, which is trickier. Okay, I got a few tricky questions here. And then later we do, you have to do for yourself a paper 5. I won't have time to do that with you here. Paper 5 is A2, right? Which you have to do. I've got about 20 more minutes or half an hour more to go through what I plan to do. Okay, now here. Okay, let's say I got here 5 experiments. Now this will make you think a bit. Okay, experiment 1. Okay, which means I now put inside here a container. Okay, experiment 1. Alright, this is the gauge of the pressure. And I put inside here number of moles of oxygen is equal to 1 mole. Okay? Temperature of this experiment is held constant 25 degrees centigrade. Of course, in this case here, if the pressure is to 1 atmosphere, the volume is equal to 24 dm. That's not. Okay, 1 mole. Okay, right? So if I were to increase the pressure, okay, increase the pressure, the volume will decrease it. So Boyles Law. So if Boyles Law happened like this here, for experiment 1 and this graph here, I would draw a graph like that, okay? Not very good, huh? Let me draw again. Okay. Draw again, draw nicer. Now actually I need to draw nicer in the sense I put the P here. 1. Okay, what's the volume it occupies? Okay, 24/dm³. Yeah, so not too good, sorry, lower better. Sometimes it doesn't work. I don't know what's happening. It's harder. Okay, it's working, right? Never mind. Okay. Now let's say, right? Can't get perfect out. Never mind. Okay, draw. Right. Let's say the volume is here. 1 atmosphere. Better to here. Okay, this is 24. Okay, so the first experiment will be like that. Yeah, this is experiment 1. Okay, that means I keep the number of moles constant and temperature constant. Yeah. Okay, experiment 1. Okay, now experiment 2. I get 1 mole of experiment 2. Okay, I get here. I put it in, so here 1 mole of oxygen. Okay, but the temperature I keep constant at 35. Okay, right? Of course, 35 of course will occupy a big pressure is one atmosphere. Of course, it will occupy a bigger volume as well because expansion, Charles' law actually. Okay, the volume here is equals to is 24. This volume here is 35. Right? Okay, so then I keep this constant. This constant, I change the pressure up and down. Okay, so how will it look like for Boyles Law? Okay, how to put this onto this graph? Very simple. Look at for 1 atmosphere, that's 1 35, isn't it? So you follow Boyles Law. So 1 atmosphere, it will be 35 somewhere here. Okay? So 35 here. Of course, it will be also inversely proportional. Okay, this will be the graph for experiment 2. Remember, the number of moles and the temperature remain constant for the experiment 2. So about experiment 3? Experiment 3, 2 moles, okay, 2 moles, and this one here, 25. Right, so at 25, 2 moles here, right, 1 atmosphere, this one here. So how will it look like? Remember, see, it increased, the number of moles increased the volume, but the pressure remains the same. Okay, so how will it look like in the graph of Boyles Law? 1 atmosphere, 48. 1 atmosphere, 48. Okay, 48 here. 48. And of course, it will follow what law? Boyles Law. Of course, they will be like that. Must hit here. Okay, this is experiment 3. Do you understand? So they ask you to draw on each of them if they follow Boyles Law. Number 4. So oxygen 1 mole. And lower the temperature to 15. Of course, the volume occupied will be smaller because gas will shrink on. Okay? So 23. 1 mole, 23. See here. 23. So the 4th experiment will be like that. Also Boyles Law. Okay, number 4. Number 5. Let's say I put on a different substance. Okay? Chlorine gas. Here all oxygen gas. 1 atmosphere, same as it. Any gas amount RTP occupies the 24 dm cubed and RTP is it. So same. So where would the graph be? Same as who? Same as 1, is it? Right? Same as 1. So here be same as 5. Understand? So these are all the 5 experiments we do for Boyles Law. Looks like this. So you must know where the thing will go. Take the first one first and then compare with the rest of them. Now this PV against sun here. Of course, PV for the first experiment is how much? P times V, 24, isn't it? So it'll be 24 here. Okay? Whatever, 24 here. It's 24. Why? Why 24? 1 times 24. Okay? So second one is 1 times 35 and so forth, so forth. So it's, the second one is 31 times 35 up here. This is experiment 1. Experiment 2 is 35 here. Experiment 3, okay, because it's a constant, is it? 48. Go and think about yourself. Don't just, I just tell you now. You don't think I'm always correct, okay? Number 4 is lower than is 1 over 23 is 23 here. So the PV value will change, right, for each experiment because the temperature change, right? Okay, but for every experiment, the temperature don't change. That's why it's constant here. Why it change here? Because the temperature change, you know. Okay, but when the temperature remain constant, like this one here, this and this constant here, right? They have the same value. You know. See, 5 is here. This is 4. This 5 is here. Clear? Okay. So graphs are very important for you to understand. Now, first is on 1 over V. Of course, 1 over V, you can see here 1 over V, right? This is the graph of 1 over V. Remember that 1 over V, proportional, right? Because 1 over V, let me refresh your mind. 1 over V for 1 is 1. 1 over V is 2. 1 over 0.5 is 2. And 3 is 3, so it's proportionally. Okay? So here you will have like this graph, P against 1 over V. You see this later in paper 5. Okay? Yeah. So you want to draw this 5 diagrams to here. Okay? Right? First, of course, right, sum 0. If there's 0 volume, 0 pressure. So let's say, let's try that. Experiment 1. Experiment 2. Right? For this one here, for 1 atmosphere, for 1 P, 1 over V will be smaller, is it? Because 1 over 35 is smaller one. So 1. Okay? Let's say it's 1 here. Okay? So it's 1 2, it will be smaller, isn't it? right? One here is smaller than here. This is the first one, right? Smaller. So here, so be, okay, oh, sorry. Okay, that's not, okay, works very well now. Okay, be from here, okay, x2. See now, right? 1 over v, p is 1, isn't it? For both experiment, 1. Okay, 1. See? So next one is 1 over v is 1 over 48, even smaller. Okay? So smaller. 1 over 8 is smaller still. Okay, so now okay, here's 3. Okay, so this one is 23, bigger, isn't it? Right? 1 over v is bigger. So 4 is bigger. So let's go back to pressure for 1 versus constant. Yeah. Okay, so be from here to here. 4. Obviously, for number 5, it's the same as 1, isn't it? Okay, right? 5 is 1. 5 is same as here. Okay, so our first one here you can do for yourself. Okay, rho over p. Okay, so here. Remember rho over p. I did it with you here. You can go and think for yourself. Oxygen. Remember, see the rho over p value, right? Depends on the mr and the t. If oxygen is constant, right, 32, 32, 32, 32, then the t will be the one that will play the part. Okay, now, okay, t remember is okay over this plus this one here. So for the first one is 107. The second one is what the temperature is higher, right? Divide by a smaller value, right? Temperature here is the same. It's the same as this. Temperature is lower, of course lower still. Okay, okay? So get different. They are constants. Okay, think about it, right? Remember, rho over p is dependent only on mr and the t, right? So this is the first time that the 5 is not the same as 1. Because why? For chlorine, the mr is bigger. That's why it's not the same. Okay? Right? Now, before I go to this part here, 10 more minutes, I want to show you how to do the calculations. I feel this is a quite interesting calculation. Okay? So that's our Boyles Law. Now, the first one is page 50. I give you the type. I won't do all. I give you a type. It can appear. That's not here. All right. Question 8. I've done it here. These are all on Boyles Law and the gas law constant. 2 grams of hydrogen at room temperature T and volume V excess pressure P. Now, when it's a hydrogen here, see hydrogen has got 3 isotopes. H11 is got hydrogen. H or D12 is got deuterium. 313 is got tritium. This is form 5, okay? I hope you know. Okay? So when it's hydrogen, it means H or H2 or D2 or D2. Okay? So the first one here, if I want to draw it up nicely, I can go here. There's got some space here. I put it smaller so I can draw more. 2 grams of a sample of hydrogen at temperature T and the volume V exerts pressure P, which means to say that, well, I've got here. I'll draw it small enough for me to fit all inside, okay? I put inside here, right, a mass of H2 is equal to 2 grams. Okay, the P, it says to be produced is pressure P, small p here. The temperature is T, and the volume here is V, okay? These are the fixed values they give you. Now here, of course, what is the number of moles of H2? 2 over 2, is it not? Because 1 mole of H2 is 2, so it's 1 mole here. So it's 1 mole here, right? We have a pressure P, temperature is T, and volume is V. Now second one, the deuterium is 1, 2, okay? Right, and here you put 2 grams of deuterium of V2. What's the pressure they ask you? Okay, now I'm going to draw here so that I can have more space, okay? Right, remember here they say what? VO2, Okay, I got half of the volume here. It's V over 2. Okay, pressure here, I don't know. Okay, what I put here? I put here is 4 grams of deuterium. 4 grams. Mass of deuterium, D2, 4 grams. So number of moles of deuterium is equal to 4 over 4, is equal to 1 mole. Temperature is also T. Now, this temperature, see? Okay, same temperature. So same temperature, 1 mole, same temperature, volume is half, the pressure is what? It's 2P, is it? Higher pressure, ma? No. So cannot be P, right? Says here, exit, okay? Which of the following exert a pressure P? Cannot be. Next one. 1 gram of hydrogen, 2 grams of deuterium, volume V. So I draw again. The drawing will help you to see clearly. A picture paints 1,000 words. Okay. Here's PI. Okay. Here's the pressure. Okay. So the volume is V, temperature is T, and here the mass of hydrogen is equal to 1 gram. So the number of moles of hydrogen is equal to what? 1 over 2, 0.5 moles. Okay. So here, and 2 grams of deuterium. Oh, sorry, the volume is 2V. I know the volume is V here, sorry. 2 grams, okay? So mass of D2 is equal to 2 grams. So number of moles is 2 over 4 is equal to 0.5. Total number of moles is 1, isn't it? 1 mole. Okay? So 1 mole of gas at volume V and T, what's the pressure? Same as it. P1. Same as here. So, right? Because it doesn't matter what kind of substance it is, as long as the number of moles is the same. See now? So C is a good answer. All correct answer. Now, here, D. Okay, now D, if I draw here, remember, double the V, okay, big V. Oh! Okay, here's what? V, 2V, the volume is 2V. Here's P here, what did I put inside here? Right? It says here 2 grams of hydrogen, mass of hydrogen, 2. So number of moles is 2 over 2 is a 1 mole. Okay? So mass of deuterium, how much is it? Mass of deuterium is 1 gram. 1 gram. So number of moles of deuterium is equal to 1 over 4, 0.25 moles. Okay? So for total number of moles is 1.25 moles. For it to give a pressure, right, you must have 1 mole, 2 moles here, 2 moles at for 2V to T temperature to give you to P, is it not? But it's less than that, is it not? See? So it's be, the P will be less than P. Is it not? So it cannot be the answer. So it's C answer. You can figure out yourself here, you can do the ratioing and see. Okay? Quickly out of 5 minutes. Okay, next one. Right? 50, then 53. These are quite interesting questions. Okay, now here, this is a normal calculation question, which I think you come up, you all can do one. Okay, using an experiment as gas syringe, right? 10 gram, 0.1 gram of gas found to occupy. So let's draw a syringe. Okay, the syringe, okay. Okay, it's a plunger. Okay, right? So the mass of the gas here is equal to 0.10 grams. The volume here is equal to 83.1 cm cube. Okay, pressure is 1.0 10 to the power of 5 pascals. Okay, temperature is equal to 27 degrees centigrade. Now remember to use P because NRT. You must, the R is given in your data book is 8.31. To use this value here, your temperature must be in Kelvin. Okay, pressure must be in pascals. Volume must be in meter cube. Otherwise cannot use. Okay, so you got to do your conversion properly. Right? So they ask you for the MR. So you can convert this to PV equals to M over MR or AR RT. Okay, so MR is equals to mRT over POV. So could do a conversion here now to cm cube, isn't it? Remember, meter 100 cm is equals to 1 meter. So remember, 1 meter times 1 meter times 1 meter gives you 1 meter cube, isn't it? Do a simple one. So it's 100 cm times 100 cm times 100 cm gives you 1 meter cube. Or 10 to the power of 6 cm cube, equals to 1 meter cube. So to change this to meter cube is 83.1 divided by 10 to the power of 6 meter cube. Or I put on here, mR equals to mass is 0.1 times R is 8.31 from the data word times T is 27 plus 273. So how much? 300. Over P changes to pascals is okay. I will change 1.4 times 10 to the power of 5. So what is your thing here? So it's the 83.1 times 10 to the power of minus 6. That's all. So don't have to do it, just check. Okay, I think this is the answer. That's all. Simple as that. So this is quite simple. Okay, this straightforward calculations. Now one more. Okay, 54. 54, I think it's a whole time to do all this because it's an interesting one. Okay, here, this is okay. Now, here we'll make use of the idea of ratio. Okay, I'll just quickly do that, okay? Most modern cars are fitted with airbags. This work on decomposing of sodium azide. This sodium azide. Okay, right? Azide actually is sodium nitrite. Okay, not nitrite, sorry, azide. Blah blah blah. Blah blah blah. Now here, remember, 2 moles is to 3 moles is to 2 moles. We are interested in only nitrogen. Okay, so moles is important. So here, this grams. So the number of moles of sodium azide equals to the mass 50 over, and what is your azide? Let me just quickly put here. I got it down here. So it will be faster for us. Okay. MR is 65. Okay, 65. So it's equals to 1.15 moles. Okay, so 2 moles. Remember this one here. So 1.15 moles is to how much is 3 moles? Here would be equals to. Oh, now my okay. Sorry. What am I doing here? No, so I'm trying to hurry and then I got all the mess. Here's not one. Here the value here is. Okay, look at the clock. Here, of course, here is this is not 1.5. This is what you do when you get hurry. Okay, now okay, here is 0.77. Okay, it's 0.77 moles. So 2 moles give you 3 moles. 0.77 moles give you, what I got here is 1.15 moles of nitrogen. Okay, so very simple at room temperature and pressure. Okay, room temperature and pressure. Okay, temperature, RTP. So 1 mole of hydrogen at RTP occupies 24 dm cube. So 1.15 moles of blah blah blah, 2401 times 1.15 is equal to, actually I got it here, 27.7 dm cube, which is C. Okay, I think I better stop here because time is up. 1 hour. I got few more questions which I will do with you later. Quite interesting question on Boyles Law. The next one, of course, I will do on Boyles Law and we have Charles' Law, and we would talk about deviation. Hopefully, we can finish on with the Dalton's Law, partial pressure. Okay, so let's see. I stop recording first. Bye bye.